Hello, my name is Dean Banerjee, and I'm with the Texas Instruments High-Speed Signal Path Division, specializing in clocks and synthesizers. Today we're going to be talking about some of the practical issues and various tools we have available to help you in your design process. To assist me, we have a power supply here, an E5052 phase noise analyzer, and an LMX2581 evaluation board. Here on the evaluation board, we have the LMX2581 synthesizer. We have an output connected to my phase noise analyzer. We also have the unused side of this differential output terminated with a 50 ohm termination. This particular output has an inductor as a pull-up, which allows the high output power. Also on the evaluation board, we have an LED to indicate the device is locked. We also have 100 megahertz crystal oscillator. And there's also the ability to use a different oscillator, such as the LMK4800 series, clock conditioners, or anything else you might choose to use. This board is connected to the computer using this cable and going back to the CodeLoader software. On the CodeLoader software, we start with our 100 megahertz input frequency, divided by 5, get to my 20 megahertz phase detector frequency, and then I program my output frequency. The charge pump gang I can program by right mouse clicking to make it go down or left mouse clicking to go up. I can change the fractional denominator and the numerator as I please. If the output frequency is going through the divider, this is the divided frequency here. But before we get too excited about hooking this up, we first have to make sure we're communicating with the device. So if we go to the port setup tab, we need to make sure we have the proper communication mode. In this case, I'm using the USB interface board. If you're using something else, be sure that that's selected. The port setup here and pin configuration is based on the evaluation board instructions. If you're having problems getting the thing running, one of the first things you should do is ensure that you're actually communicating with the device at all. For instance, if we look at the green LED light on the board, right now it's set to show the lock detect if the V-tune voltage for the VCO is in the proper range. So high would indicate the device is locked. We can actually invert that to mean low is locked. So by clicking this bit, we can toggle this on or off. So this gives us an indication of programming that would work even if the synthesizer had some other issue or there was invalid reference or whatever it was. Some other diagnostics you might take interest of is actually changing the current. You can do this by changing the programming mode. For instance, right now the device is powered up, but I can power this down. So now you see I'm drawing 30 milliamps. The reason this is not 0 milliamps is it's actually drawing about 30 milliamps from the 100 megahertz crystal reference on the board. So if I power it back up, it draws about 187 milliamps in this mode, and this is in the low output power mode. If we look at some of the other things we have the mode, which allows us to pick the external or internal VCO. You can choose the outputs to be the channel divider or the VCO, or FN, which is for external VCO. You have settings for the charge pump bleed, which is for optimizing the spurs. We have fast lock settings, lock detect settings. The fractional modulator actually has several settings here. If we right mouse click on any bit, we can see what the function of that bit is. For this one, we can program the dithering between weak, medium, strong, and disable. The fractional order, you can program 1, 2, 3. For that, the lock detect pins can be configured to output various functions on any of these pins. The VCO frequency calibration can be configured in many ways. If we start with the VCO select mode, it automatically picks the VCO core. So you can say use the last VCO core selected, which is good if you're changing small frequency amounts. If you're changing over wide frequency range, you might want to start with a VCO select choice, which is actually specified up here. And by doing this, you can actually speed up the lock time of the VCO calibration. The other thing it does, it gives you more consistent spurs and VCO gain because you pick the preferred VCO core, if at all possible. We have this bit here allows us to pick the cap code which it starts at, which is used to speed up the frequency calibration. On the outputs, we can power them up or down. So one of the mistakes I sometimes see is that the wrong output is powered up, so be sure not to make that mistake. You can program the output power as we see fit. Some of the other things, we have the registers tab. So this shows all the information that we're programming to the device. If you want to program all the registers, just hit load device and it will program them all at once. And you can also get the same thing by pushing Control L. On the burst mode, what we would do here is we'd select a value here, and then we'd pick a new frequency here. So I just happen to know that the R0 register is the one that contains the frequency information, and I'd hit run. And here it's going to go back and forth between these two frequencies on there. So going into some of the other tools, we also have the clock design tool, which is useful for simulation and also design. So if we go over to this tool, we can set up our various frequencies. Here's 100 megahertz in, 20 megahertz phase detector, select your charge pump current gain. You can select your loop filter, you know, if you had whatever it is, you can type it in. Or if you want to design, you can automatically design with this mode, or you can select your loop bandwidth and phase margin here. You can actually change around with the poles. You might want to have a dynamic idea of what that does. So if we go here, we can actually change the pole ratios around, and we can see the impact that that has. If you knew your filter, you could actually type it in like so. Or if you forgot your filter but have it saved, which is the case here, you could just load it in. So once you have a design loaded, you can simulate the performance of the VCO and the phase noise of the PLL. So this shows you that actually the VCO phase noise is what's dominating even at closer in offsets. So we might be interested in some of the performance here. So if we go over to my phase noise analyzer here, let's just compare. So at 1 kilohertz, simulation says about -91, and the actual measurement I'm getting is about -93, -94. So you see the simulation is not overly optimistic. At 100 kilohertz, I simulate -109, and I measure -111. So that's just some of the things there. If we want to look at the spurs, we have to pick a fraction that's not 0. So we can see here, and we can see the impact of the phase noise and the dithering and the modulator order. So we can simulate these effects on there. So today we've seen the power of the clock design tool as well as the CodeLoader software. For more information, including schematics, application notes, and my PLL book, visit the following web addresses. Thank you for watching.